All right, so today we're going to talk about a couple leftovers with OLS regression, and we're going to introduce logistic regression as well today. So there are some instances when you will be running an ordinary least squares regression, and you'll get some results, and maybe the results look a little wonky, they don't really make sense, they might not even fit the literature as we know it. Often when this happens, it really points to some potential violations of the OLS regression model. So the three most common OLS regression errors or violations to the model are listed here. The first is multicollinearity. So this basically tries to get at whether or not X and Y are the same concept, right? So here's an example. We talked before about correlations and whether or not variables are highly correlated with each other. Now, typically, if a variable is highly correlated with a phenomena that happens to be your dependent variable, that's usually good news. However, if the independent variables are closely related to each other, highly correlated with each other, that's not good news. That basically means that you're counting the same concept twice in your model. So if you're trying to explain voting by including both education and income, turns out education and income are highly correlated with each other, and the OLS regression model doesn't know which of those two is actually having the impact on voting. In fact, it winds up being whichever is entered first. And if you switch them around, you'll get differing results. This sort of instability is a problem. It turns out it's a fairly minor problem, but it's one that we can really address. One, you can diagnose this by looking at your correlations matrix. If you haven't already done one by now, then we obviously need to have a talk, but if you haven't done one by now, do a correlations matrix, look at how your independent variables relate to each other. Typically, a correlation coefficient of 0.80 or higher is a very serious problem. These are very closely related. Now, this could also vary depending on the size of your sample. The smaller your sample, then the lower that bar might be. It might be 0.7 instead of 0.8. So sometimes we have to make a judgment call, but typically 0.8 or higher, you're talking about high levels of collinearity or multicollinearity. The solution, if you identify this, is to simply remove one of those offending variables. It really means you need to really be thinking about the theory that motivates your model, right? Multicollinearity can be a problem, but luckily it's a very simple one to solve. Remove one of those variables. End of story. Heteroscedasticity. This is one of my favorites, and if we were actually in class, I would spend a whole lot of time on this, including how to spell it. There is some debate about how to spell it. I'm spelling it the way you see it here. Heteroscedasticity basically refers to the presence of non-spherical error distributions. Translation, are the errors in your regression model, remember there is an error term that you're calculating there in that regression line, are those errors systematically located in one space? Okay, so for instance, if you're drawing that regression line, right, imagine an X and a Y axis, and you've got points everywhere on that axis, and you're drawing a line, right? Now, if you've got a lot of errors only on one end of that line, let's say at the highest values of X and Y, or the lowest values of Y, for instance, or the lowest values of X. If you've got a lot of errors only in one part of that picture, then it means that there may be something systematic about that error pattern, right? So that's problematic too. It really means that your OLS model is failing to pick something up. Maybe your explanation is incomplete. Maybe there's a whole lot of different stuff that's going on there. Typically, what we do to identify heteroscedasticity for us is we can run a plot in Stata. It's called an RVF plot. It's a residuals versus fitted plot, and it basically shows me where I plot my line in my regression line and where my residuals are. As a general rule of thumb, we're looking for a fan-shaped set of errors. So narrow on one end, right, all the dots closely related to each other on one end, and really, really dispersed on another end. It looks like an open fan. Well, the problem here for our purposes in this class for Political Science 310 is we really don't have a solution that's easy for this particular problem. I like to consider this data cancer. It is the end. You can identify that you've got heteroscedastic error, which means that there's some systematic error issues in your regression model. You can think a little bit about what you might be missing in the model, what you should have included, those sorts of things, but there isn't really a technical solution that we address in this class. The solution to heteroscedastic error is one that is a little bit more complex. It's outside of our toolbox, and it is something that we would usually cover in an advanced course. So for our purposes, is if you have and you identify heteroscedastic error, you identify it, you tell that this is what's going on here, and you say, well, can't do anything about it right now. Okay, the third is the potential presence of influential observations, right? So is there an observation that is drawing your OLS line up or down? One of the things that we know about averages or means is that it's really easy to draw up that mean. Well, in OLS regression, because we are ultimately taking sums of squares, it is also possible for an observation to draw that line up or down artificially. Consider it the Bill Gates of observations, okay? There are two ways to know if you have this or to diagnose this, and one is to do a diffits. This command in Stata will produce a new variable in your data set, and you're generally looking for values, diffits values that are higher than 2. You can also plot it. An LVR2 plot is a leverage plot, which if performed correctly, will actually allow you not only to identify whether or not you have a high influential observation, but also which one it is. So we can actually label them so we can identify, oh, that's Brazil 1972. Figures, because it's always Brazil. All right, so the solution there is to remove the offending observation if at all possible. Now, often what winds up happening is it's possible that you remove one observation and another one winds up becoming influential. So you have to really think about whether or not it makes sense to remove that observation, or maybe think more about your sample. All right, we'll get a chance to practice those things in lab, but I did want to spend some time introducing logistic regression as well. So logistic regression, as I mentioned before, closely related to OLS regression, but it is slightly different in that logistic regression is used when the dependent variable is binary or dichotomous, right? So there's only two categories for that dependent variable. There's a 0 and there's a 1. What else do you need to run a logistic regression? That's it. It doesn't matter what your independent variables look like. It's only the dependent variable that matters for this particular model or method. Logistic regression is known as a linear probability model that estimates the probability of an outcome, right? When your y is 1, on the dependent variable. There are only two values possible on that y. A logistic regression is interpreted differently than a multiple regression or an OLS regression. I'll show you in a minute why this is the case. Largely, this is because logistic regression or logits transform the dependent variable to log odds. In other words, they change y to a probability that ranges from 0 to 1. Oops. So instead of using these sums of products and weights and actual values to predict the values on the predicted line, the y, as in OLS regression, in logit the value that is predicted is a probability ranging from 0 to 1. So logistic regression specifies the probabilities of a particular outcome, let's say vote or don't vote, for each case or each observation involved. And in case you're curious right now, what you're looking at is the basic algorithm, the basic meat underneath this particular model. It's a simple probability equation that depends on a cumulative logistic distribution function where z will range from negative infinity to positive infinity, p ranging from 0 to 1, and these are related So for instance, here we're looking at the probability of a 1 occurring or voting, which looks like 1 over 1 plus the exponent of negative z1. Z1 is located here. Looks similar to your regression equation, very similar. But again, remember, we're looking at probabilities here versus the probability of not voting or getting a score of 0 on that dependent variable. Okay, I'm not testing you on this basic formula, but just so you know, this is known as a very simple probability or maximum likelihood estimation. That's what we're focusing on here. And for logistic regression, generally speaking, what we're talking about is an algorithm that is fairly simple. It's the Newton-Raphson algorithm that lies underneath the hood, and it depends on this basic probability calculation. Lots of really cool factorials in it. Anyway, for those of you who are curious. All right, so the interpretation of a logistic regression model is not intuitive, especially when you're looking at logistic regression coefficients. In order to interpret them, you have to specify a value for each variable and use the resulting coefficients to predict the probability of y being 1. The coefficients, therefore, do not on their own indicate the magnitude of the relationship between an independent variable and the dependent variable, only the direction of the relationship. So they're not going to be giving you a whole lot of information. You'll be longing for the days when you had it very easy and all you had to do was look at an OLS coefficient and use the simple robot language, or you can get real fancy and ask for margins to give you even more information. But with logistic regression, those coefficients are not directly interpretable. They're not intuitive at all. I should also add that goodness of fit measures in a logistic model are also not intuitive, and you have to actually ask Stata to produce additional figures for that model. You'll get a pseudo R-squared, which is similar to what we see when we're looking at a goodness of fit model in OLS regression, but it is not really that useful. So you have to ask for additional information to know how well the model performs in classifying the cases correctly, and also providing more information on those coefficients. So you're going to produce a logistic regression model, and then I'm going to tell you, okay, now we're going to try translating this in Stata. How do we do this? Particularly when it comes to coefficients, we'll use margins or margin commands to try to understand how the independent variables impact the dependent variable. In order to assess the magnitude of a relationship, you must calculate the predicted probability or odds ratio to examine, or you can examine a graphical representation of the relationship. Now, the nice thing about Stata is that it allows us to ask Stata, after we've produced the logistic regression model, to give us the predicted probabilities. We could also get odds ratios, but I try to avoid those. They're not really that helpful in terms of really identifying cause and effect in a clean way. We can also ask Stata to produce a graphical representation of the relationship between x and y, which is really, really nice. So we'll spend some time playing with margins next, and we'll also talk about goodness of fit measures for those logistic regression models. So those are the key things. So now you've got some basic understanding. Remember, logit is only for those dichotomous dependent variables. All right, see you next time.